Which will kill you, volts or amps? Voltage or current? You may have heard the saying, it's not the volts that kill you, it's the amps. In one way that's true, but as you'll see, that's not the complete story. You can't have amps without volts, and resistance plays a part too. What are current and amps? Current is just a measure of how much charge passes a point over a period of time. It's in units of amps. In this example, you can see negatively charged electrons. The amount of current, or amps, is the amount of the negative charge of the electrons passing this point every second. Here's a table used in a few government's health and safety documents, telling you what happens to your body when different amounts of current flow through it. It's for both 50 and 60 Hz alternating current, or AC. That's what you get from your wall socket in many countries. For direct current, or DC, the current has to be higher, but the numbers are still in the milliamps. According to the documents, at 1 milliamp, or 0.001 amps AC, the feeling is barely noticeable. But above 16 milliamps AC, or 88 milliamps DC, your muscles are stimulated to extend and flex. But when the flexing dominates, you can no longer let go. At 20 milliamps AC, your respiratory muscles, the ones responsible for breathing, are paralyzed. That of course leads to death. The heart's pumping is controlled by electrical stimulation. At 100 milliamps AC, or 300 to 500 milliamps DC, if the current runs through the heart, then that is interfered with. This causes what's called ventricular fibrillation. The heart quivers instead of beating properly, and also leads to death. So far, it does look like it's the amps that kills you. But current doesn't move on its own. That's where voltage comes in. The current needs energy in order to move, and it's the voltage that supplies that energy. Voltage can be defined as the amount of energy for each unit of charge. The volt is just a unit for voltage. A little energy applied to each charge would mean a lower voltage, and a lot of energy applied to each charge would mean a higher voltage. When traveling through the body to go to and from the heart, most of the charge passes through the blood vessels. The bloodstream is a relatively good electrical conductor. The big barrier is the outer layer of skin, made up of dead skin cells. That skin layer resists the flow of charge. It plays the part of a big resistor in the body's electrical circuit. As the name implies, resistors resist the flow of electricity. Let's look at an analogous electrical circuit. This motor represents the heart, these wires are the blood vessel, and these resistors are the dead skin that provides most of the resistance to the flow of current. The values of these resistors add up to 100,000 ohms. That's the same resistance that a body with dry skin has. We'll use household electricity, which here is 120 volts AC. When I plug in the electricity, the motor doesn't turn. That's good. That's analogous to the heart being protected by the skin resistance. The general rule is anything above 30 volts may be hazardous. But the skin resistance doesn't stay constant. The higher the voltage is, the lower the skin's resistance is. And at only around 450 to 600 volts, the skin will break down altogether and allow electricity to easily pass. It'll no longer act as much of a resistor at all. And voltage isn't the only thing that affects skin resistance. So does wetness. If the skin is wet, from water poured on it, from sweat, or from high humidity in the air, the body's overall resistance drops from around 100,000 ohms to around 1,000 ohms. So here I replace the resistors so that the resistance adds up to only around 1,000 ohms. Now when I plug it in, the motor turns. That's analogous to more current flowing through the heart. So with wet skin, the resistance is lower, causing more current to flow, more amps. How long the current flows also has an effect. At 50 milliamps, if you manage to let go within 2 seconds, then you'll be okay. But if the current is 500 milliamps, then you have just 0.2 seconds, 0.2 of a second, to let go and still be okay. What about when you get a shock by rubbing your feet on carpet and then touching a metal door handle? There could easily be a few thousand volts there, enough to break down your skin's resistance. But while there is enough voltage, there isn't a lot of charge in this case. However, since it's all being dumped at once, it can result in a high current, or amps, but only for a brief amount of time, around 1/1,000,000th of a second, or 1 microsecond. So the fact that it doesn't last long makes it harmless. The same applies to this small homemade Wimshurst machine. The voltage can be in the thousands, but the current is small and lasts for only a short time. That's not to say that a brief shock can't cause some harm, like a moment of pain as it burns your skin. I wouldn't want to get a shock from this big Van de Graaff generator, or from my homemade high voltage power supply. Or worse yet, from the high voltage, high current coil on this microwave oven transformer. Well, thanks for watching. See my YouTube channel, rimstar.org, for more informative videos like this. That includes one on how to make the homemade Wimshurst machine I showed, another on how fast an electron or electricity flow down a wire, And for variety, one on how to use a Fresnel lens from a rear projection TV as a solar cooker, or just have fun burning stuff. And don't forget to subscribe if you like these videos, or give a thumbs up, or leave a question or comment below. See you soon!